Good morning. It's Tuesday morning, I think. We're going to get into chapter 28 and chapter 29 by probably by the end of Thursday or Friday, and that will more or less conclude the course. So you have all problem assignments for those chapters. I will upload solutions to the most recent chapters. We'll have one more take-home problem set, and then I'm thinking about what to do with the final. So uncharted waters, but we'll muddle through. Okay. So so thus far you are really familiar with the following two problems. If this is the surface of the Earth, and here we know that the gravitational potential energy reference is 0 joules. And if we have an object of mass m at some height y above the surface of the Earth, we know lots of things about that problem now, right? So we know that there's a gravitational force. Know that there's a gravitational force equal to mg down toward the center of the Earth. We know that there's a gravitational potential energy here, which is mgy. And we know if that ball is let loose, it will accelerate downward with some acceleration given by the gravitational force. So we know lots about this problem, right? And we can talk about lines of equipotential and all kinds of things that we previously discovered and used by analogy when we were talking about electrical phenomena, right? So these would be lines of gravitational equipotential. Okay, and so we used that pretty extensively in analyzing the analogous electrical problem. We know that if we establish a parallel plate arrangement of charge, and I should point out before we actually move to that problem that there are gravitational field lines which are pointed downward again toward the center of the Earth, and so moving over to the analogous electrostatics problem. We generate a parallel plate arrangement of charge, same amount of positive charge on the upper plate as negative charge on the bottom plate. If we were to place a positive charge, say, at this position, again, we know a lot about that problem, right? We know that there are electric field lines. We know that there are electric field lines between the plates, electric field lines. We know that they are constant as long as the plate separation is small relative to the length of the plates. And again, that's to suppress what are called fringing effects. Okay, and so we know that there is in the electrical force on that charge, which is going to be given by Q times E. We know that there are lines of equipotential, electrical equipotential, and again, this is mathematically identical to the gravitational problem. So we know lots about the gravitational piece and the electrostatics piece. We know that the electrical potential energy then is going to be Q times V. And again, these two problems are analogous, right? So again, these are lines of electrical equipotential. Beautiful. So now, in this chapter's discussion, unlike the electrical development where we started with Coulomb's law, and from that we developed a picture of electric fields. In this chapter, we're going to assume that the magnetic field already exists, and how it comes about is the material for the next chapter. But we're going to assume that magnetic fields already exist. But before we launch into that, I want to just make a couple of observations. One is that, as you know, charge comes in two flavors. Right, in two flavors. Right, positive charge and negative charge. And even though it seems common sense to us, because we know lots about chemistry and now lots about electrostatics, right? We can actually have naked positive and negative charge. Right? We can have an electron which is far away from any other charges, and hence we can have it all by itself, right? We know that in the universe that charge is conserved, but we can certainly form negative charges. We could form a chloride ion in the gas phase and have it be relatively far away from any other positive charge. That's not true in magnetism, right? So in magnetism, we can't have isolated north and south poles. So if you've ever played with a bar magnet when you were young, if you were to take that bar magnet and somehow break it in two, so that you would have two pieces, which look something like so, then you would establish again two smaller bar magnets, each with north and south poles. And so it seems that nature has been a little weird here in the fact that we can't, at least at this moment in time, right, we can't have what are called monopoles. And that's an interesting idea. It would be good if I could spell it properly, right? So let me just erase that. So there can't have monopoles. That is, you can't have an isolated. Can't have an isolated north or south poles. Now that's another quirk about this material, is that we talked about positive and negative charge, but we retain an antiquated way of describing magnets in terms of north and south poles. Okay, and we're just going to retain that. So there are some theories that predict the existence of monopoles, but as of this YouTube video, there has been no experimental evidence that has concluded that monopoles exist. And again, it's a rather interesting area of research. It resurges every now and again with a couple of experiments that people have done, but again, the experimental evidence is lean at best in even indicating that monopoles exist. So anyway, as of right now, no monopoles, which is very interesting. Okay, and again, for those of you who might be a little more interested, you can check it out on at least starting with Wikipedia. So the problem at hand then is the following: we are going to we are going to assume that magnetic fields exist. If we look between the poles of a magnet, again, you can look up some pictures online. We are going to assume here that there's a magnetic field between these poles. By convention, magnetic fields are going to start or emanate from north poles and will end or terminate on south poles. And if these poles are large enough in extent, then we're going to assume that the magnetic field is constant and homogeneous between the poles. And the designation for magnetic field is capital B. And so it is a vector quantity. And we'll get to the units of it a little bit later. So it's a vector quantity. And what we're going to need to explore is the analogous problem that we looked at in gravitational fields and in electric fields. We're going to place a charge. Let's just put a charge here of positive Q. And we're going to ask ourselves what happens. Right, what happens now if we let that charge go? All right. So let's write that out explicitly. Right. What happens when we let this charge go? And the answer is surprisingly nothing. Right? Nothing happens. Nothing happens. That's interesting, because if we were to put a mass in a gravitational field or a charge in an electric field, in each of those instances, right, a force would be felt, and that particle, be it mass or charge, would accelerate. However, we have the very interesting scenario here that the charge does absolutely nothing. So let's change the experiment now, and let's take a look at this experiment. So now what we've done is drilled a hole through the north and south pole, small hole. And this time, again, we can't forget that we have magnetic field between the poles, and we're going to take our positive charge now, and we're going to shoot it. All right, so we're going to shoot it right down that hole that we drilled through the poles. Okay, and so we have a velocity vector now, which is parallel to the magnetic field vector. Now, you know, if you did this with a charge between parallel plates, that while the charge was in the electric field, it would be accelerated by the electrical force. And you can use one-dimensional kinematics to do all kinds of calculations on that. As a matter of fact, you did that on exam number 2. So here we have the analogous problem. We're shooting a charge, right, along the direction of the magnetic field, and we ask ourselves what happens. And again, interestingly enough, if we were to analyze the velocity with which this charged particle exits the south pole with, we would realize that that the velocity is unchanged. That is, neither the magnitude nor the direction has changed. The velocity has remained constant. I don't know what just happened here. There we go. The velocity is constant, and so there was no effect. Conclusion: no effect by the magnetic field. Okay? Now, that's pretty interesting, because right now that's in stark contrast to either the gravitational problem or the electrical problem. All right? So now I'm going to end with just setting up the next scenario, right? And again, I don't want these to get too big in time, because then they get hard to move these files around. So here's North Pole. Here's South Pole again. We have magnetic field. We have magnetic field between them. Okay. And this time, however, what we're going to do is we're going to take our positive charge, and we're going to shoot it into the field this way. So now what we have is we have a scenario where V is perpendicular to the magnetic field. Okay? Now when we meet again, I'm going to reorient this. I'm going to reorient the picture, and we need 3 dimensions in looking at magnetism, and so that will provide some challenge for those of you who have a hard time thinking in 3 dimensions. It might be the same issue you had in organic chemistry when you were looking at enantiomers, and you needed a model set, right? And which really helped. And so here you're going to need to use all 3 dimensions as well. And we have some prescriptions on using your right hand to help with that visualization. And so we're going to have some what are called right-hand rules for magnetism. But we'll get into that next. And so stay tuned for part 2. All right, see ya.